Hi everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at another separating technique called chromatography. So hopefully by the end of today's lesson what you'll be able to do is to describe what chromatography is and explain how it actually works. To start us off though, let's have a little look back at our previous lesson and have a go at answering these 3 starter questions in your books for me. Let's mark those answers then. So question 1, the process we were looking for is simple distillation, or if you just wrote distillation, you would get the mark for that. Question 2, the piece of equipment is a condenser. And for question 3, the process is fractional distillation. This time you need both words to get that mark. So add it up, score out of 3, and give yourself your score in your books. When we're talking about chromatography, the first thing we really need to know is, what does it even mean? Now, if we break the word chromatography down, as I've done in the bottom left of your screen there, we can see that the word chroma is actually meaning colour, and then our graphy just refers to the fact we're going to make a graph. So basically, chromatography is making a colour graph. And the way that this works is it's going to rely on 2 different chemical phases. We're going to have the stationary phase, which is the bit that's not going to move. And then we've got the mobile phase, which is the bit that's going to move. And where we're talking about this word phase, that's just a substance that's in a solid, liquid or gas state. And the reason we'd use chromatography is to separate out mixtures of things like inks and dyes, food colourings and bits like that. So it's really important that you know those phrases, stationary phase and mobile phase, because this is one of those common multiple choice questions that I've seen crop up over the initial few papers. So you need to know stationary phase does not move, mobile phase does move. So I'll leave this up for about another minute so you've got a chance to jot down those points in your book. So when it comes to actually carrying out chromatography, you probably need to know about 3 different ways we could do this. So the first one is the one you've almost certainly done at school, which is good old paper chromatography. So where we're talking about paper chromatography, then our stationary phase, the one that doesn't move, is the bit of filter paper, and the mobile phase, the one that does move, is going to be the water that's going to be in our beaker. So what we actually need to do then is set up our chromatography, and you do need to know how to do this. So what we're actually going to do is, first of all, on our bit of filter paper here, then we're going to measure up from the bottom about 2 centimeters. And then using a pencil, very important we use a pencil here, then you're going to put a little horizontal line 2 centimeters up from the bottom of your filter paper. Okay, so what we end up with is a little pencil line 2 centimeters up from the bottom there. Now that's going to be our starting point. So what's going to happen is we're then going to get a bit of our sample. So we're going to pick our pen, whichever we want to look at, and we then put a spot on that bottom line. So all we're going to do then is have our little spot on our bottom line there. And the idea being that you're going to use a couple of different pens in order to do this, so you've got a couple of different spots to look at. So that when we actually finish, what we end up with are 3 different samples. So there we go, we've got our 3 samples there. And if you really want to, using your pencil again, you can label them A, B and C, okay, just so you remember. Now what we're then going to do with our bit of filter paper is we're going to place it into our beaker, and there's a few different ways that you could have been taught to do this. Very simple way is just to fold it over the edge of the beaker. You may have been told to attach it to a splint that sits in top of the beaker, maybe across a pencil, anything really that's just going to stop it from falling into the water completely. Now what we need to make sure of, we've mentioned the fact that we've got some of this water, is that when we have our water and our little filter paper in the beaker, that it doesn't actually reach those spots. So when your little bit of paper is sitting in there, we don't want the water coming up above those spots or touching them, we want it just at the bottom. So realistically we're looking at about 1 centimeter depth of water in the bottom there. So what we've got is our water in the beaker, and when we actually place our paper in, you can see it's not actually going to touch those spots. So then what we're going to do is just place our filter paper into our beaker, and we just leave it. That's quite simply how we do that one. Now the idea behind this is that we're going to watch and see what happens to those spots of ink. Now in theory what we should find is that they're going to be pulled up, that bit of filter paper, and separated out into their individual colours. Now we obviously need to leave it for a while for that to happen, but don't leave it too long so that the water doesn't go off the top of the filter paper. Okay, we need to stop it when it gets within a couple of centimetres of the top of the filter paper. So after 5 minutes, when we take our chromatography paper out, we end up with something like this. So hopefully what you can see on there is the fact that we do have these different coloured blobs that represent the different inks that we've got there. Now the key thing with this is we need to actually be able to calculate something called the RF value. Now what we need for this are a couple of measurements. The first one is the overall height of the solvent. So you can see that's where we've actually got to, okay, so where the water gets to, and put a little pencil mark on there for that. And then when we're actually measuring the spots, on your exam paper it's going to be a lot easier because they're going to give you really clear spots. But on this we'd actually be aiming for the middle of any of those particular coloured blobs. So they're the 2 values we need, and we're going to have a look at how to calculate the RF value in a moment. But from this we can obviously see we've got 3 different pens here, because obviously we've got different colour splodges. So you've got a little red and pinky splodge there and a blue one. This one is just a pinky colour one, and then we've got a yellow and a blue on the far end. So we've got 3 different colour pens there, but we could always work out if it was the same pen, because if the actual patterns match, it's the same. The second kind of chromatography that we could use is a process called thin layer chromatography. Now what we find here is the actual way it's done is very similar to our paper chromatography, But as opposed to using a bit of filter paper, what we actually have as our stationary phase is a thin layer of silica or alumina powder which is spread over a plate of either plastic or glass. So basically we've got a sheet of glass or plastic, and then on the surface of that is silica or alumina powder that's been adhered to the surface so it doesn't fall off when you pick it up. And then what we're going to do is place our sample onto the powder. We then place the plate into our solvent, as you can see in the diagram there, and it moves up just like we saw on the filter paper. So a similar process, but using a different stationary phase here. The third type of chromatography we need to know about is gas chromatography. So in the diagram at the top we can see the setup of the equipment we would use. On the far left we've got our carrier gas. Now that is going to be our mobile phase. It's the carrier gas that's going to move through the rest of the machinery. If you look a bit further along, you can see at the top it says sample injected here. That's where we're going to add our sample to the gas chromatogram. Then we can see that that tube comes down into this coil. Now packed within the loops of that coil are particles of our stationary phase. And the stationary phase is again that silica or alumina powder that we did have on our TLC plate. This time it's packed into that metal column. Then you can see at the end of that little coily area, we go back up into the detector, and that's going to actually detect the different chemicals passing through. That's connected onto the computer where we get the chromatogram on the screen. So what we actually find is this is just a different way to carry out chromatography, which we use for other samples. So the stationary phase is the silica or the alumina powder packed into that metal column. The mobile phase is that unreactive carrier gas, and we tend to use a gas like nitrogen. So if you want to do a sketch of the diagram, by all means pause the video and give yourself a chance to do that. There's obviously going to be the PowerPoint up on the website later, so you could always just take a copy and print it out. And then what I'd like you to do is make sure you've got the stationary and the mobile phases written down, and then see if you can answer that question at the bottom: why is nitrogen used? So I'll give you about another minute and a half to do this. The reason that we use nitrogen as our carrier gas is because it's what's known as an inert gas. So inert just means it doesn't react. So by using it as a carrier gas, it's not going to react with our sample, it's purely going to use it to carry it through the rest of that column. So what we've got here then are 5 sentences all about how gas chromatography works. To help you out, the missing words are in the bottom right corner of your screen. So what I'd like to do is write down those 5 sentences and fill in the blanks using the missing words in the bottom right. So I'm going to give you about 4 minutes to do that. Let's make sure we got those words in the right places then. The sample is turned into a gas when it's injected into the column. The carrier gas pushes the sample through the column. Different components take different times to travel, depending on how strongly they bond to the stationary phase. The detector sends a signal to the computer as each component leaves the column, and that produces the chromatogram. So give yourself a tick for each of those words you got right, and then give yourself a score out of 6 next to it. Obviously, if there were any you got wrong, make sure you have written the correct word in so that you do have a full description of how gas chromatography works. One of the things they could ask us to do when looking at chromatography is to calculate a value called the RF value. Now, in order to work out the RF value, it's a very simple division. We do the distance travelled by the substance divided by the distance travelled by the solvent. So to give you an example, we've got a little diagram in the bottom left there with spots A and B. So A is the green spot, B is the blue spot. And if we had a question that asked us to calculate the RF value for the blue spot. So what we would need to do is measure the distance from the baseline to the centre of the blue spot first of all. So in this case it's 3 centimetres, it's labelled on our diagram. Then we need to measure the distance from the baseline to the solvent front, so the little mark on the paper where the solvent got to. And again we write down how far that was in centimetres. What we then do is we use our formula, distance travelled by substance divided by distance travelled by solvent. So in this case our substance has moved 3 centimetres, so it will be 3 divided by the distance by the solvent, which is 12. So 3 divided by 12, put that into your calculator and you get an answer of 0.25. Now there are no units for RF values, all you need are the numbers. So that's our worked example. If you want to write it in your book, obviously do jot those points down. I will leave it up for about another 10 seconds, but if you need longer, just hit pause on the video. Okay, your turn. What I'd like you to do is go through that same process but calculate the RF value for the green spot this time. So I'm going to give you about a minute and a half to have a go at that one. So let's make sure we know how to do this question then. We need to calculate the RF value for the green spot. So what we're doing is we're only looking at this one this time, the green spot, which is spot A on the diagram. Now we still use our formula at the top here, the distance travelled by the substance divided by the distance travelled by the solvent. So we need to find the distance travelled by the substance first, which is this 8 centimetres. So that is our 8, and we're going to divide that by the distance travelled by the solvent. So from the baseline to the solvent front is 12 centimetres. So 8 divided by 12. Now if you type that into your calculator, you get a value of 0.6 recurring, which we may well do to 2 decimal places, which would be 0.67. It doesn't have units, it's literally just the number there. Now on an exam paper, if they were to give you something like this without the measurements, then you measure from the baseline to the centre of the spot you're looking at. So just remember that it's always from the baseline, whether it is the spot or the solvent front. So from the baseline to the centre of the spot or to the edge of where the solvent gets to. Then use our formula up here and hopefully we got 0.67. Give yourself a tick if you got it right. Now, one of the things we need to know is whether a sample is pure or not. Now, if we think back to our earlier lesson, a pure sample is one that consists of only a single chemical. Now, chromatography is one of these processes we can use to determine if a sample is pure. So write down that first sentence and then see if you can suggest how this would work. Hopefully what we said there is that if it's a pure sample, it will only have a single spot on the chromatogram because it won't separate out. If there's only one chemical, we're not going to have more than one spot. One of the other questions they could ask you on chromatography is looking at a comparison between the thin layer chromatography, TLC, and paper chromatography. And what we've got here are the 4 key reasons why thin layer chromatography is better than paper chromatography. First of all, it's quicker. Secondly, it's more sensitive, so that means we only need a very small sample in order to analyse it. Thirdly, we can actually use a larger range of stationary phases and solvents, so that means that we've got different solvents that may obviously work with thin layer chromatography that won't with the paper chromatography. And we can then, once we've actually carried out chromatography, remove a single spot from the TLC plate, because remember, it's just powder on a surface, so you can just scrape that little spot off and then we can analyse it through gas chromatography to find out what it actually is. So make sure you've got those 4 reasons TLC is better than paper chromatography in your books. I'll leave it up for about another minute. What we've now done then across the past few lessons is had a look at a range of different separating techniques, and we use those different techniques to separate different things from one another. So what I've given you here then is a little table that's only half finished. We've got a mixture containing different things on the left. I want you to tell me what separation method we should use. So remember, we've used a whole range over the past few lessons. Think about which one is best to separate each of those. So I'm going to give you a couple of minutes to have a go at that in your books. Let's check our answers then. So if we've got an insoluble and a soluble substance, then we're going to use dissolving followed by filtration. Because if we've got a mixture of a soluble and an insoluble substance in a beaker, then what we need to do is dissolve the soluble one first. So that means we'll have a dissolved solution and insoluble solid floating in there. We then carry out filtration, which means we will be left with the insoluble solid in the top of the filter paper, and we will then have our soluble substance in the beaker. We can then obviously carry out crystallization to get that back. A solute dissolved in a solvent, then this is going to be crystallization to get the solute, or if we wanted to get the solvent, we'd use simple distillation. So go careful when they ask you how would we get the solvent, don't say crystallization, because obviously crystallization, we're evaporating the solvent off, it wouldn't get it. So we need to think, if it's the solute, it's crystallization. If it's the solvent, it's distillation. Third one, 2 or more substances in the liquid state, then that is our fractional distillation. And then finally, coloured soluble substances, this is our chromatography. Either paper or thin layer would work there. So add up your score and give yourself a mark out of 4 for that one. Obviously, if you'd like to jot down any of the points on there that you didn't get right, or that you think are actually valuable extra detail that you didn't get, then just hit pause on the video and give yourself a chance to get those points written down. Last thing to do then are the plenary questions. Those with target grades up to grade 5, it's the 2 columns on the left. Those of you with a target grade of over a grade 5, it's the 2 columns on the right. So I'm going to leave these up for about 2 minutes today, but if you need longer, just hit pause and take as long as you need. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.